So we have a U group here. G is U of 32, which is all the positive integers less than 32 relatively prime to 32. So that's all the odd numbers, all the odd positive numbers less than 32, since 32 is a power of 2. And we've got this subgroup H of G. It probably would be a good idea, not that you had to do this, just to figure out, to confirm H is a subgroup, we should confirm 15 squared is 1. 15 squared is 225. What's 225 mod 32? If you divide that by 32, you get a little over 7. Subtracting 7 from that and multiplying by 32 emphasizes that the remainder is 1. So yes, for 15 squared, mod 32 does equal 1. This is a subgroup of G. And since G is abelian, it's also going to be a normal subgroup of G. In fact, H is a normal subgroup of G. In abelian groups, all subgroups are normal. So it's only questionable whether a subgroup is normal or not if G is non-abelian. In both cases, we still consider these factor groups, also called the quotient groups, as really a key tool in abstract algebra for understanding things. Dealing with cosets is important in group theory. It's also going to be important in ring theory as well. Our goal is to figure out, what is this factor group isomorphic to? This is the factor group of G by H. I say G mod H for short. Many people do, actually. It is kind of, in a way, similar to modular arithmetic in the fact that you're really dealing with equivalence classes. You're working with equivalence classes just like you are in modular arithmetic. If we were to try to figure this out without thinking about the orders of individual elements, how could we do that? Is that possible? Maybe, maybe not. Back in chapter 8, there's a fact that you should know for the exam that U of 2 to the n power, a power of 2, if n is greater than or equal to 3, was isomorphic to the external direct product of z sub 2 to the n minus 2 with z2. That was a fact back in chapter 8. Maybe you remember it, maybe you don't. So in our case, n is 5, U32 is isomorphic to what? 32 is 2 to the 5th. So we need a 2 to the 3rd here, and 8. External direct product with Z2. That's not a cyclic group, by the way, right? It would have to be, since 2 and 8 are not relatively prime, this would not be isomorphic to Z16. That's a fundamental fact to know from chapter 8. You can't combine these into Z16 because 2 and 8 are not relatively prime. So, okay, is that helpful? H is a 2-element group. It's obviously isomorphic to Z2. When I do this factor group, when I consider this factor group, can I is it possible I can do something like this? Take the external direct product of Z8 with Z2, mod out by Z2. Is it possible I can cancel the Z2s? You might wonder that. Is that possible? I'll put a big question mark here. Maybe it is, maybe it's not. You might hope that's true. Maybe that would justify the fraction notation. I suppose if we do not get Z8 here, that would imply this is not possible in general, though maybe it's possible in some circumstances. Okay, that's not so clear. First step, which many of you did, is figuring out what are the elements of this factor group. They are cosets, left cosets as a default, though you could take them to be right cosets if you wanted to. There's H itself, which could be thought of as 1H or 15H, right? Because we know AH equals H if and only if A is in H. That was a property of cosets back in chapter 7. a fundamental property of cosets. So 1h and 15h both equal h because 1 and 15 are both an h. All right, that takes care of representatives 1 and 15 in front. I've got 14 more representatives to think about. How about 3h? What is that? By definition, that's the set of all products. 3 times 1, 3 times 15, 3 times everything in H. Mod 32. So that's 3, and 45 mod 32 is 13. 3 and 13. So you could also write that as 13H. Though 3H is good enough. You only need one representative. So now we've used 1, 15, 3, and 13. Go on to 5, 5H. What is that as a set? It's 5 times 1. That's one element in it. And 15. 5 times 15. 75. Mod 32 is 11. All right. 32 goes into 64. Yeah, I got a remainder of 11. So that also equals 11H. The left coset of H and G containing 5 is the same as the left coset of H and G containing 11. Run out of room here. I'll have to keep going down this way. We also have 7H. Consists of 7 times 1 and 7 times 15. 7 times 15 in ordinary arithmetic is 105. Okay. 105 mod 32. 32 goes into 96. So remainder is 9. That's also 9H. Continuing down here. What's the next number in the list? How about 13? We already took care of 13. How about 15H? 15H consists of 15 and 15 squared. Oh, no, we already took care of 15H, didn't we? Sorry. That's this one. 17H. Consists of 17 and 17 times 15. Let's see, 15 squared is 225. Add on another 30, 255. 255 mod 32. Subtract 7 from that and multiply by 32. It looks like it's 31. Doing a modular arithmetic calculation in steps there. I'm trying to figure out 255 mod 32. So I divide by 32. The quotient is 7. There's some remainder. I have to figure out that remainder by taking the decimal part and multiplying by 32. So this is 31. And this also equals 31H. 1, 2, 3, 4, 5 elements so far. How many more are there? It's got to be 3 more. There's got to be 8 total, right? Because the number of left cosets is the same as the index. Remember this. This is by definition the index of G and H, of H and G, which by Lagrange's theorem was the order of G divided by the order of H. G's got 16 elements. H has got 2 elements. Our factor group has to have 8 elements. We've got 3 left. I guess there's 19H as well. What's 19 times 15? I'm trying to figure out the other element besides 19 in here. It's 285 divided by 32. Figure out the remainder. Like this. 29. Two more elements. What do I have left here? Looks like I got to also think about 21H. 21 squared, or excuse me, times 15. 21 times 15. Whoops. Mod 32, divide by 32, subtract off the integer part, multiply by 32. It's 27. 21h equals 27h. One more. 23h. I think the only two numbers we have left are 23 and 25. 23 times 15. Divide by 32, subtract 10. Times 32, yes, is 25. 23h does equal 25h. Okay, kind of a pain. If you want to be sure of everything, maybe you were able to do that quicker and you just weren't quite sure of everything. These are the 8 elements in this factor group. I wrote them each in 2 ways, and actually the first one in 3 ways, but you only have to work with them with one of those ways. You only need one representative. These form a group under coset multiplication. What's coset multiplication? Coset multiplication you multiply cosets AH and BH by multiplying their representatives. The left coset of H and G containing A times the left coset of H and G containing B, by definition, is the left coset of H and G containing A times B. That's a definition. It's a definition that you have to prove is well defined. You got to prove it makes sense. I do that in the lectures. The book does it. You should be able to do that proof too. You'll find it on page 196. Proof of this operation being well defined is on page 196. It's a big deal to prove that this operation makes sense, and it requires H to be a normal subgroup of G, not just any subgroup of G. This requires H to be normal in G. That's why normality is important. One reason is so that this makes sense. So you can prove it makes sense, and then you can use it for applications. So in the context of this problem, if, for example, we want to multiply 3h by itself, if we want to square 3h, you just multiply 3 by itself to get 9h. Is that the identity? It could be. Don't speak too fast in thinking it's not the identity of the factor group. What is the identity of the factor group? It's H itself. 1 times H. 1 is the identity of U32 as a group under multiplication mod 32. Yeah, 1H, or in general, EH, which equals H, is the identity of the factor group. Think about it. If I replace that A with an E, where E is the identity of G, EH times BH would be E times B times H, BH. EH is the identity of what? Of the factor group. And EH does equal H because H is a subgroup of G, and therefore E is in H. So does this thing 9H equal the identity? No. The identity H equals 1H and 15H. It does not equal 9H. 9H equals 7H. the simplest form for all these elements is to probably take the smaller representative. 1, 3, 5, 7, 17, 19, 21, and 23. Oh, I forgot to circle this last one. So it's not that you can't say the answer is 9H, but it would be actually be more typical to rewrite that as 7H. But it does not equal the identity. So the order of 3H is bigger than 2 as an element of the factor group. Therefore, the factor group cannot be isomorphic to the external direct product of Z2 with Z2 with Z2, because all of its non-identity elements would have order 2. It can't be that. Is the order of 3H, what are the other possibilities? 4 or 8? Keep going. 3H cubed is 3 cubed H, or if you prefer, which is 27H or 21H, or if you prefer, you could do this as 3H times 3H squared. In other words, 3H times the previous answer you got, 7H. But that also can be seen to be equal to 21H. Either way you do it, you got to get the same answer. You see that I did that 2 ways there? Got the same answer. I had to. Either cube 3, get 27, which up here, that's the same as 21H. Or think of it as 3H times 3H squared. I've already got the answer for 3H squared. It's 7H. Put that down there. If I had used 9H there instead of 7H, what would have happened? I could have done 3H times 9H, 27H. But yeah, once again, that's the same as 21H. A little confusing, but kind of fun at the same time. In a weird sort of way. How about 3H to the 4th power? I could do that as 3 to the 4th H, 81H. 81. That's not an element of U32. How do I deal with that? Mod it by 32. This 3 to the 4th is done in U32. Mod 81 by 32. 32 goes into 64. This would be the same as 17H. Done. That's an element. 17H. I did mod 32 there. I also could have figured this out as 3H times 3H cubed. I've already figured out 3H cubed was 21H. So this is going to give me 63H. Mod 32 is 29H. Right? 63 mod 32, or excuse me, not 29, but 31. 31. Looks different, doesn't it? 31H and 17H. Well, guess what? They should be the same. Yep, they are. (31H equals 17H. I also could have done it as 3H squared squared and used my previous answer for 3H squared, 7H. This is 7H squared, which is 7 squared H, or 49H. 49 mod 32 is 17. Get the same answer. If we didn't get the same answer in these things in the end, something was wrong somewhere. And is that the identity? No. The identity is this. Ah, I know the answer. 3h has got to have an order bigger than 4. By Lagrange's theorem, the only thing left is 8. I don't have to keep going. Therefore, by Lagrange, the order of 3h equals 8. Therefore, the factor group is, in fact, isomorphic to Z8. That's good enough. There's only 3 possibilities for what the factor group could be. It's of order 8, and it's abelian. I haven't proved this, but I'm claiming there's only 3 possibilities of what it could be. It could be the external direct product of Z2 with Z2 with Z2. Or it could be the external direct product of Z4 with Z2, which is not isomorphic to 3 Z2s. Z4 with Z2, you can switch those around to write the external direct product of Z2 and Z4, but that's still isomorphic. It's not a new isomorphism class. Or it could be isomorphic to Z8. It could be cyclic. In this case, it's cyclic. So at least for this example, it seems like this cancellation does work, but I'm not claiming for sure it works in general. We'd have to investigate further. You like this? It takes practice, but once you get enough practice, I hope you get to the point where you say, hey, this is kind of fun, right? Last week we had that LCM making those charts kind of fun. This week, this is supposed to be kind of fun. The theory is one thing. Reading the book and trying to understand the book is one thing. Doing calculations is another. They're both important, but maybe this one's more fun. But doing examples, doing calculations illustrates the theory, helps you believe the theory, even if you don't understand the proofs. Could we make a Cayley table for this? We could. Should we? Probably not the entire thing. But if we were to make a Cayley table, what would it look like? 1h, 3h, 5h, I'm not going to make the whole thing, 7h, 17h, 19h, 21h, 23h are ways of representing the 8 elements. And you could do the same kind of thing across the top, and then you could do calculations and figure out the rest of the Cayley table. For example, if you wanted to figure out what goes right here, where this is maybe 19h here, what goes in that row and that column, you have to figure out 7h times 19h. You multiply cosets by multiplying their representatives, 7 times 19h. 7 times 19 is what, 133, I think? 7 times 20 is 140. 133h, but then I got a mod by 32. I do want representatives that are in U32. 32 goes evenly into 128, right? 32. So it looks like that's the same as 5h. Should be a 5h that goes there. And you keep going. But again, it's isomorphic to Z8, it's cyclic.